Okay, sir. Hello. Good evening. Hello. Am I audible, sir? Hello. Am I audible?
Yes, sir.
Okay. Thank you. So, good evening, everyone. And in today's class, we will discuss about multiple integrals. And if time permits, then I will discuss some concepts of vector space. So, uh, I am your PMRF TA Shankhanarayan Chattopadhyay, and I am doing PhD at the Department of Mathematics, Indian Institute of Technology, Ropar. And you are all enrolled in the class Engineering Mathematics 1. The course instructor is Professor Jitendra Kumar, and we are learning from the NPTEL platform. So I think multiple integrals I have discussed elaborately. Now in today's class I will mostly discuss about some problems, that how to solve more problems on multiple integrals, and these problems will be effective for you to learn and more about multiple integrals, and to know and to score good in your NPTEL exam and in the assignments. So the first slide we have something called Fubini's theorem, and Fubini's theorem we have already known that Fubini's theorem for rectangle is that when fxy, the function, okay, so the so what is Fubini's theorem? That Fubini's theorem tells us that if a function fxy, and this function fxy is a function of two variables x and y, and it is defined over the rectangular region AB cross CD, then then the double integration r fxy dA, then this integration, double integration, you can calculate it by using the change in the order of the integration. That means you can do solve the problem by integrating from c to d fxy dy, and then by putting the limit on y, and finally your function will contain only one variable x, and then once again integrating a to b dx, you will get eventually the answer. And similarly for the continuity of fxy is actually guarantees us that you can also do in the other way, that is you can do that, you can first integrate with respect to x, and then put the limits on x, and then you can utilize this function which will be free from x and only contain the unknown y, and then you can integrate from c to d to get the desired result. Now we have already learned that this change in order of integration is highly helpful when we have some sort of complicated things, like if we are unable to compute this type of integral where the y is something very complicated type of function, and this a to b fxy dx is way simpler than that, then we usually use this change in integration thing. So there are some these things are not in your syllabus, you can just go through these things, that why is. So the basic properties I will just discuss, that like the integration in single variable, the double variable integral is also linear. That means if you integrate the linear combination of two functions, then that is equals to the sum of the individual integrations. So See here, example 1.1.1, we have to evaluate the integrand double integral sigma x plus y xy dA, where omega is the triangle bounded by y equals to 0, x equals to 1 and y equals to x. That means we want to determine the integration. We want to determine the integration, evaluate the integration, this x plus y plus xy, where omega is the triangle bounded by y equal to 0, x equals to 1 and y equal to x. Give me some time, I am giving you some idea about the domain of integration. Just see that first we will call y equals to 0 plus x equals to 0, and then y equal to x. I think I made some mistake. The domain of integration is x equals to 1, sorry, x equals to 1. So see, x equals to 1. Now see, this is actually our domain for integration from this triangle. Is it visible? The triangle is visible to you. This triangle is our domain of our integration, right? This triangle is our domain for integration. Now see how we will solve it. We will just like take limit. Now, y varies from 0 to x, y varies from this 0 line, y equal to 0 line, to y equal to x line, and x varies from this 0 to 1. Then we can cover this triangle, or we can use the another procedure. How? The another procedure is y varies from 0 to 1, y varies from 0 to 1 and x varies from 0 to y. That is also that will be like x equals 0 to y, that will be this x from y to 1, right? Y varies from 0 to 1, y varies from 0 to 1, and x varies from y to 1. Now see how we can solve it. Say so first of all, y varies from 0 to x. See, y varies from 0 to x. Why? Because y varies from this y equal to 0 line, that is the x-axis, and then to up to y equal to x straight line, this straight line. Okay, and x varies from this 0 to x varies to this 1. Okay, so see, x equals to 0 to 1 and y varies from 0 to x and x varies from 0 to 1. Then this function x plus y plus xy dy. Then once again we are first performing integration with respect to dy. Now if you integrate this function with respect to dy, then how it is coming? This is coming as x in integration of dy, that will be x into y, plus y dy integration will be y square by 2, plus xy dy, that integration will be x y square by 2. Now if you just put x instead of y, you will put the limit y equals to 0 to x, you will get x square plus x square by 2 plus x cube by 2 dx. And if you just calculate it, now it is simply the integration of a polynomial function, and if you just integrate this polynomial function, you will get the answer as 15 by 24. Okay, so that is something you can at least try, that how to solve this type of integrations. Okay, similarly you can use the another integration form, that is that integration form that I was telling, that you can instead of first integrating with respect to y, you can integrate with respect to x. Take integration from how integration x will be varies. X will vary from this y equal to x line, so x equals to y to x equals to 1, x equals to y to that x equals to 1, and y equals to 0 to 1. So if you solve this, you get x plus y plus xy dA, y equals to 0 to 1, x equals to y to 1, x plus y plus xy dx. And similarly if you just integrate, you will get that is 15 by 24 is the actual answer. Okay, just just read this problem, example 1.1.2. I am giving you a couple of minutes, just read this problem. And point to be noted that here the region omega is the domain bounded by y equal to x and y equal to x square. So the domain is from bounded by y equal to x and the domain is y equal to x square, right? So evaluate the integral this omega 2 plus 4x dA, where dA is nothing but dx dy, where omega is the domain bounded by y equal to x and y equal to x square. Okay, now let's see that how this domain is governed by y equal to x and y equal to x square. Once again, just go to here, y equal to x and y equal to x square. Oh, y equal to x, so equal to x square. See, so this is actually our domain of integration here. Is it visible? This line, this slice, this is enclosed within y equal to x and y equal to x square. Is this visible? This slide is our domain of integration. Okay, so this is so this slice is our domain of integration here, that this slice. And how this limit is varying, you can take the integration y equal to from x equals to 0 to x equals to 1 and then vary y from x square to x. Okay, that will be easier for you to handle. Now see how they are solving. They are solving, yes, x equals to 0 to 1 and y varies from x square to x, because here if you see that the integration is from x square to x, that is this slide one, right? So that is this slide is actually you have to in this portion you have to actually integrate it. So the limit for x will be from 0 to 1, the limit for y will be, this is y equal to x square card, this green one, and this red one is actually y equal to x card. So in between this slice is actually you have to integrate the function. And if you are to determine the area, sectorial area by this bounded region, then you, instead of that fxy what is given, this 2 plus 4x, you just put here 1, that is integration omega dx dy, that will give you the required sectorial area between the two curves. Now see 2 plus 4x dy and y varies from x square to x. Now if you integrate 2 plus 4x with respect to y, you will get 2y plus 4xy. Now just first put x, so 2y plus 4xy, it will give you 2x plus 2x square, 2x plus 4x square. Now you want to minus with respect to x square, so then 4x square minus 2x square minus 4 into x into y, that you have to put y equal to x square, then it will be minus 4x cube. So that will be 2x plus 2x square minus 4x cube. And if you want to integrate, then you have to just integrate with respect to x, and this integration 2x dx is x square, integration 2x square dx, it is 2x cube by 3 minus 4x cube is integration is actually x to the power 4. So that is how you will eventually get that there will be 2 by 3. And similarly, because of the regularity property of this function of the domain omega, you will eventually get that similarly we fixed x and varies y. Similarly, conversely, we can do by fixing y and varying x. Now see, in this curve your x is varying from 0 to 1 and your y is varying from x squared to x. Now you can also conversely you can try it, that is it is lying on the positive quadrant, the sectorial area is lying in the positive quadrant. Now you vary y from 0 to 1 and vary x from y to square root of y. So that will be your answer, that is x equal to y to square root of y. And if you just compute this function also, you will get the answer to be 2 by 3. Okay, now we have to determine, that is another problem. That problem we have to determine that find the area bounded by y equal to 2x square and y square equal to 4x. Now they are actually two parabolas. They are two parabolas. And how do they look? I am just plotting y equal to 2x square, y equal to 2x square, y equal to 2x square and y square equal to 4x. And y square equal to 4x. So they are the two parabolas. See how the parabolas are looking like that. So this is your domain of integration. So this is actually your, see, this is actually your domain of integration, this intersection, this thing, and they intersect at 0 0 and they intersection at 1 2. Sorry, y equal to 2x square and y square equal to 4x. Y equal to 2x square. Here this, and I think this problem is that there is one typo here. Y equal to 2x square. The intersection points are not 0 0 and 1 1. The intersection points are 0 0 and 1 2. The intersection points are 0 0 and 1 2. There is one typo there. Y square equal to 4x and y equal to 2x square. Y square equal to 4x and y equal to 2x square. There will be one typo, that will be not 1, that will be 1 and 2. Now we have to integrate the area. So we are like we will keep x as fixed and vary y. Now see, this is already bounded in the first quadrant, so all things will be positive. So x will vary from 0 to 1, x will vary from 0 to 1 because this is 1 2 point, this is 0 0 point, and y will vary from this green curve, y equal to 2x square to y equal to square root of 4x. Square root of 4x means 2 square root of x. So that is how we will compute that. Similarly y, so y varies from 2x square to 2 square root of x, and we have to find the area bounded by this. So just we have to integrate dy dx. If you integrate dy, you will get 2 square root of x minus 2x square. Once again you have to just, it will be just a definite integral which we are considering only one single variable x, and that problem you can easily solve from integration 0 to 1, 2 square root of x minus 2x square. That will be nothing but 2 by 3. So that is how you have to determine the area bounded by two parabolas. Similarly, you can try by combining different functions and how they intersect and all, and you can determine the sectorial area inscribed between the two curves. Okay, now we have to find the volume of the solid under the paraboloid z equal to x square plus y square over the bounded domain R bounded by y equal to x, x equals to 0 and x plus y equal to 2. So how we will how I will See how to y equal to x, x equals to 0, y equal to x, x equals to 0, y equal to x, x equals to 0, x plus y equal to 2. So sorry, this is y equal to x, x equals to 0, this is y equal to x, x equals to 0, that is x plus y equal to 2. So how we will integrate here? You have to integrate between this triangle 0 2. So there are three vertices 0 2 0 0 and 1 1. So this is actually your domain of integration, right? This is your domain of integration. From y will vary from 0 to 2. Now see, there will be, you have to partition this problem into two parts. How you have to partition this part? See, okay, no need for partitioning, we will vary it from this. Okay, see, we will vary x from 0 to 1. So if we vary x from 0 to 1, so we are taking this entire slice here. Now we have to vary y. So y varies from y equal to x to y equal to 2 minus x. Then if you just vary x from 0 to 1 and y from x to 2 minus x, then you will integrate it and you will get the governing result. See, x varies from 0 to 1 and y varies from 0 to x to 2 minus x, and you have to integrate this. Here the function is z equal to x square plus y square. Just put here x square plus y square dy, and if you integrate it x square dx, that integration, first you have to integrate with dy, so that will be x square y plus y cube by 3, x square y plus y cube by 3, and the limit will be from y equal to 0, y equal to x to y equal to 2 minus x. Now just put here y equal to x and y equal to 2 minus x. Now it is your home task. It is very simple. You have to first expand this 2 minus x whole cube into binomial term, and then you have to just integrate it from 0 to 1. That will be your answer. Is it clear that how we have considered that varying x from 0 to 1 and y is varying from x to 2 minus x? That is actually our domain. See, x varies from this 0 to 1 and y varies from this line to 2 minus x line. So that is your integration region. Okay. Next problem is also an interesting one. We have to find the volume of the solid bounded above by the surface z equal to x square and below by the plane region R bounded by the parabola y equal to 2 minus x square and y equal to x. So that is nothing new here. You have to just integrate this x square, and you have to first determine that which two points, this 2 minus x square and x, they actually intersect. Now 2 minus x square and x, they intersect at the point x equal to 1 and at the point x equal to minus 2. Because if you put y equal to minus 2 here, you will get x is equal to minus 2, and also y equal to 1 is your one integration, another intersection point. So just vary x from minus 2 to 1 and vary y from x to 2 minus x square, and just integrate this x square dy dx. How the domain of integration looks, I am just plotting for your kind reference. Y equal to 2 minus x square and y equal to x, y equal to x and y equal to 2 minus x square, y equal to x and y equal to 2 minus x square. See, here this portion is actually our domain of integration. Is it visible? This is the portion where we have to integrate. Got my point? This is the portion where we have to integrate it. This portion. Now they actually intersect at the 2 points -2 and 1 1. So first of all, x varies from -2 to 1 and y varies from x to 2 minus x square. So that is the your curve on the xy plane that is intersected by one parabola and intersected by the straight line y equal to x. Now see, y varies from x to 2 minus x square. You have to integrate x square. So x square into dy, that integration will be give you x square into y, and x square take y common, x square common, and if you just put limit y equal to x, then it will be 2 minus x square minus x, and then it is very simple that x square 2 minus x square minus x dx, it is just a Riemann integration, definite integration of a function of a single variable. I think easily you can easily handle this part. That will be your home task to solve this with respect to integration with respect to x. Now how the change using Fubini's theorem, how the change of integration works, this problem will give you that answer. Consider the evaluation of integral r sin x by x dA over the triangle formed by y equal to 0, x equals to 1 and y equal to x. Since this can be extended as continuous function over r by the basic properties of Riemann integral, the function is integrable. Now by Fubini's theorem, how you will integrate it? Just put that has only problem at x equals to 0, at the x equals to 0 point, and if you take limit x tends to 0 sin x by x, and we know that this is very standard result and the answer is 1. So that function has continuous extension all over the domain. Now you have to just use Fubini's theorem and you have to determine the value of integral does not depend on the order of integration because it is a continuous function. As we noted earlier, r is regular in x and y. If we take it as x regular, that is you have to keep y as y between constant range and x between variable range and try to evaluate the integral. Then what you will get? If you take the value 0 to 1, that y value from 0 to 1 and x value from y to 1, then this integration you cannot solve. This is very difficult to evaluate. You cannot evaluate this integral in this form, right? Now however, just implementing Fubini's theorem, you will just take it as x equals to 0 to 1 and y equal to 0 to x. Then just you can integrate it, the sin x by x dx, you are integrating with respect to y, so there dy integration will be y. If you put x, you will be sin x dx, and sin x dx, that will be, if you take integration, that will be minus cos x, and if you integrate it, you will get minus of cos 1 minus of cos 0, minus of cos 1 plus cos 0, and cos 0 is equal to 1, so the answer will be 1 minus cos 1. Okay, and there is also one problem, that how to determine this type of integrations. We have to determine the integration 0 to infinity e की power minus ax minus e की power minus bx by x dx, where a and b are greater than 0. Now you see that this integration is nothing but, you can write it that the okay, I am giving you 2 to 4 minutes that how to evaluate this integral. I'm just giving you 2 to 4 minutes. Just quickly go through the slide that evaluate the integration 0 to infinity e की power minus ax minus e की power minus bx by x dx. This integral is equivalent to, so e की power minus ax, e की power minus bx, you can write, if you just integrate this e की power minus xy dy, you will get the answer that this is nothing but integration 0 to infinity a to b e की power minus xy dy dx. Now the domain of integration is the infinite strip, that x varies from 0 to infinity and y varies from a to b. Now if you change the integration order, you first integrate with respect to x, and if you take the change the integration of order, that is integration x varies from 0 to infinity and y varies from a to b, then it will be e की power minus xy, e की power minus xy, and that will be e की power minus xy will, if you integrate with respect to x, you will get as e की power minus xy divided by e की power minus xy divided by minus y, e की power minus xy divided by minus y. And if you still integrate it, I think there is some typos here. If you still integrate it, you will get it e to the power minus xy dx integration 0 to infinity. You will get it as minus e की power minus xy divided by e की power minus xy divided by e की power minus xy divided by minus y, e की power minus xy divided by minus y. Now if you put the limit 0 and infinity, you will get it as e की power minus y. You will get the answer as e की power minus y by y. So the answer will be e की power minus y by y. Now you have to just use some substitution, and if you take substitution, you will get the answer. There will be one b minus a extra term here. I think that term is missing here. Okay, I will solve it and I will post it in the NPTEL group. I think there is one typo here. Double integrals in polar form. Now similarly, instead of Cartesian coordinate systems, we can move to the polar coordinate system, spherical polar coordinate system, and we can simply evaluate the area common to the cardioids r equal to 1 plus cos theta, r equal to 1 minus cos theta. And since the region is symmetric with respect to x axis and y axis, how to r equal to 1 plus cos theta, r equal to 1 minus cos theta. Okay, r equal to 1 plus cos r equal to 1 plus cos theta and r equal to 1 minus cos theta. See, so you have to integrate in between. So they are actually two inverse cardioids. This type of structure is actually called cardioid. So that is actually the cardioid, and you have to integrate along this cardioid. Okay, and the limit will be from theta equals to 0 to pi by 2. Theta equals to 0 to pi by 2, r equal to 0. This region is symmetric with respect to x axis and y axis. The required area is thus, you have to just multiply with respect to 4 and see the elementary area in polar coordinate, that is not simply dr d theta. Instead of simple dr d theta, it is r dr d theta. So the limit for integration will be 4 into integration theta to 0 pi by 2 and r equal to 0 to 1 minus cos theta r dr d theta, and you just simply integrate it and you will get the answer. Evaluate r3 dy y dA. R is the region bounded below by x axis and above by the cardioid, r equal to 1 minus cos theta. Now see, so here also r equal to 1 minus cos theta. See, r equal to 1 minus cos theta above the x axis. That means you have to determine the domain of integration is these things, right? Your domain is the entire this domain, And now how the cardioid evolves? This cardioid evolves like for r equal to 0, that is for r equal to 0, that is 0, that is 1 minus cos theta. So r equals to 0, that is 0, and as theta increases from 0 to pi by 2, you cover this sectorial area up to this, and from pi by 2 to pi you cover this. So that varies from theta varies from 0 to pi, and r varies from 0 to 1 minus cos theta. So that is what they are implementing, that 3y actually when you transform from Descartes Cartesian coordinate to polar coordinate, then x is written as r cos theta and y is written as r sin theta. So that is r sin theta, r dr d theta, because in elementary area of polar coordinate is actually the elementary area is actually r dr d theta. Now it is simple calculation, that r square sin theta dr d theta, you just integrate it, you will get the answer. Now we will prove that we have to evaluate I equal to integration 0 to infinity e की power minus x square dx. Now we have to recall one thing, that I equal to 0 to infinity e की power minus x square. Oh, forget about this thing. Okay, this thing I think something, using Fubini's theorem we may write I square equal to, that is I into I, that is 0 to infinity e की power minus x square dx, 0 to infinity e की power minus y square dy. So if you combine it, you will get integration 0 to infinity e की power 0 to infinity e की power minus x square plus y square dx. Now if you take this integration, so if you represent this in polar form, your region of integration will be r varies from 0 to infinity and theta varies from 0 to pi by 2. Therefore the above integral becomes integration 0 to pi by 2 for r the limit will be 0 to infinity e की power minus r square r dr d theta, and if you integrate it you will get pi by 4. So that is the answer, that integration 0 to infinity e की power minus x square dx is pi by 4. Next is volume integrals. For volume integral the idea is same, but instead of like 2, you have to evaluate 3 successive integrations. So that is one problem, that you have to find the volume of the region bounded by the surfaces z equal to x square plus 3y square and z equal to 8 minus x square minus y square. So how we will integrate it? See, the volume is V and the integration is taken from the triple integration omega dz dy dx, where omega is bounded above by the surface z equal to 8 minus x square minus y square and below by the surface z equal to x square plus 3y square. Now you have to take the projection of omega in xy plane, that is the solution of 8 minus x square minus y square equal to x square plus 3x square. You will get x square plus 2y square equal to 4, and hence your limit for y will be minus square root of 4 minus x square by 2 to the power square root of 4 minus x square by 2, and x will value here, put y equal to 0. If you project it in y equal to 0, that is x line, you will get x square equal to 4, that is x varies from minus 2 to 2. Now this is 8 minus 2x square minus 4y square, this integration dz, you have to just, it will give you z, and 8 minus x square minus y square minus x square minus 3y square. If you calculate it, you will get 8 minus 2x square minus 4y square dy dx. Now integrate with respect to dy. If you integrate with respect to dy, you will get 8 minus 2x square into y minus 4 by 3 to the power y cube, and then you put the value of y. Okay, if you put value of y, and here the integration is simple, just put x equal to 2 sin theta. If you put x equal to 2 sin theta, you will get this answer. Okay, there is one more problem on volume integration. So see, the idea is, if you have two surfaces as z equal to phi xy and z equal to psi xy, that is z equal to phi xy and that is z equal to psi xy. Now first task will be to determine the projection of the surface on the xy plane. So if you take the projection of the surface on the xy plane, first you have to put z equal to 0, and so x square plus 3y square plus equal to 8 minus x square minus y square. Psi xy equal to psi xy will give you the required interval for y. Now once again, if you want to integrate with respect to x, you have to just put y equal to 0 in this relation, and that will give you the corresponding limit with respect to x. So here see, you have to find the volume of the region bounded by x plus z equal to 1 and y plus 2z equal to 2 in the first quadrant itself. Okay, so you have to find the region bounded by x plus z equal to 1 and y plus 2z equal to 2 in the first quadrant. So first you have to put z equal to y minus x, and here z equal to 2 minus y by 2. If you just take this, that z equal to 1 minus x, so if you just see here, that draw line parallel to z axis and note that the upper surface are 2z plus y equal to 2 over triangle bounded by x equals to 0, y equal to 1, y equal to 2x and z equal to y minus x over the triangle bounded by this. And therefore you can just integrate it, that z is varies from 0 to 2 minus y by 2, x is varies from 0 to y by 2, y is varies from 0 to 2, x varies from 0 to 1, y varies from 2 to 0 to 2x, and z varies from 0 to 1 minus x. Here the limit for integration is dz dx dy, here the limit for integration is dz dy dx, and simply you will just integrate it and you will get the required answer. Now if you just move to example 1.1.1, that is the order of integration. Evaluate z equals to 0 to 4, y equal to 0 to 4, x equal to 2y to 2, and the limit the integration is 2 cos x square by square root of z dx dy dz. Now note the projection of omega onto xy plane is the triangle bounded by projection, that is, if you just put that is that thing, that is that varies from y equals to 0 to 1, x varies x equal to 2 and x equal to 2y. So changing the order of integration in x and y, you will get this as z from 0 to 4, x from 0 to 2 and y from 0 to x by 2. See how we are, see y equal to 0, x equal to 2 and x equal to 2y. See y equal to 0, x equal to 2, y equals to 0, y equal to 0, x equal to 2, y equal to 0, x equal to 2, x equal to 2, and x equal to 2y, and x equal to 2y. So that is actually our, this is actually our x projection on the xy plane. Now see how they, if you just integrate in the following order, that y varies from 0 to 1 and x varies from 2y to 2, y varies from 0 to 0 to 1, and x varies from 2y to 2, x varies from 2y to 2, then the integration will be difficult to handle. Now how can you change the order of this integration? Take x varies from 0 to 2 and y varies from 0 to x by 2. Y varies from 0 to x by 2, x varies from 0 to 2. Okay, now integrate with respect to y equal to 0, x by 2. If you integrate this, that will be dy. So 2 into dy, and that is x by 2 limit, so that will be 2 into x by 2 will be x, and that will be cos x square. Cos x square, x cos x square. Now just take x square equal to any variable, x square equal to t. So t, x equals to 0, t equals to 0, x equal to 2, t equal to 4. So that will be cos t into dt by 2 square root of z into dz. Then just integrate it with respect to t, and then finally with respect to z, you will get 2 sine 4. Now there is one more interesting problem, that when you substitute in multiple integrals, you have to use the concept of Jacobian. We have to evaluate the integral I where x varies from y varies from 0 to 4 and x varies from y by 2 to 1 plus y by 2. That is actually the domain of integration is a parallelogram with vertices 0, 0, 1, 0, 3, 4 and 2, 4. One has to divide the domain into 3 domains. Instead we can take the transformation u equal to 2x minus y by 2 and v equal to y by 2. Then the inverse transformation is x equal to u plus v, y equal to 2v. And how you determine the Jacobian? You determine the Jacobian by j equal to del xy, where x is a function of u and v, y is a function of u and v. You have to just determine del of xy by del of uv, and your Jacobian is done. So there are several problems which by using this evaluate the integral and all, you can integrate, use the Jacobian formula, and you can try on your own. Now example 1.2.3, evaluate the integration r dA by 2 minus x square minus y square by 2 over r, where x square plus y square is less than or equal to 1. Now see this function, if you try to integrate with respect to the Cartesian coordinate system, this integration is very very tough to handle. Now you can clearly substitute this using the polar transformation. You can substitute this using the polar transformation, and you can solve it easily. See now x is the transformation, x is equal to r cos theta, and y is this transformation is y equal to r sin theta. Now the Jacobian is, first you have to take derivative of this x with respect to r. If you take the derivative with respect to r, you will get this cos theta. If you take derivative with respect to theta, you will get minus r sin theta, and this r sin theta, if you take derivative with respect to r, you will get sin theta. If you take derivative with respect to theta, you will get r cos theta, and if you integrate it, if you solve this determinant, you will get r. Now just use the substitution formula. Here the domain of integration is the entire circular disk. I am plotting the circular disk. You will just see how x square plus y square looks. See, this is x square plus y square equal to 1, that is the circle. Now if you just put r equal to 1, you will also get the circle, that is r equal to 1, that is the circle, same circle. So r varies from 0 to 1, and to cover the entire circle you have to rotate this theta up to 0 to 2 pi. Okay, so that is how you will integrate it. That r, if you just put here, that's this dA term, that will be modulus of Jacobian, that will be modulus of r, and for that dA dx into dy, you will get r dr d theta divided by 2 minus r square to the power 2 equal to, so these terms are separable, so you can just put like into theta integration 0 to 2 pi d theta into r equal to 0 to r dr by 2 minus r square whole square. If you just put r square equal to t, we will get the desired formula. Similarly, you can use the transformation substitution formula for the triple integrals, and that is quite same. Suppose you have a 3-dimensional domain G, and that is transformed onto a domain D with the transformation x equal to x, u v w, y equal to y u v w, z equal to z u v w. Then triple integration f x y z dv, triple integration that will be converted into G, and that will be Jacobian of J. And that Jacobian is actually, we have to first take derivative with respect of x with respect to all u v w, take derivative of y with respect to all u v w, take derivative of z with respect to all u v w, and then take the modulus, because here you have to put the modulus term. So there are problems, I am excluding these things, you can actually check them. So there is some problems that cylindrical and spherical coordinate systems. So a cylinder point P in the space R cube is represented by r theta z, where r theta are polar coordinates of the projection of P onto xy plane, and z is the distance of the projection from P. When you take the transformation x equal to r cos theta, y equal to r sin theta, and z equal to z, the Jacobian is, first this prime denotes partial derivative with respect to r, this x theta denotes partial derivative with respect to theta, and this thing denotes partial derivative with respect to z. Now if you just take partial derivatives xr, x theta, xz, so the transformation is x equals to r cos theta, the transformation is y equal to r sin theta, and here the transformation is z equal to z. Now if you take the differentiation, partial differentiation, and your Jacobian will be r. Now see how these cylindrical coordinate systems are effective for you to calculate volume integrations. Find the volume of the cylinder x square plus y minus 1 whole square equal to 1 bounded by z equal to x square plus y square and z equal to 0. So the line, so if you just use the transformations that x equal to r cos theta, y equal to r sin theta, z equal to z, your integration will be theta varies from 0 to pi, r varies from 0 to 2 sin theta, and z varies from 0 to r square, and this is your integration term r dz dr d theta. You integrate it, you will get 5 pi by 4. Similarly, spherical polar coordinate system, how they look? Spherical polar coordinate system, how they look? In the the Cartesian coordinate system xyz is converted into the polar coordinate system rho theta phi, where rho is the distance of P from the origin and phi is the angle made by the ray OP. This is this. The transformation is x equal to rho sin phi cos theta, rho sin phi cos theta, y varies from rho sin phi sin theta, and z equal to rho cos phi. You determine the Jacobian, and you will get this rho square sin phi. How they are effective? See, if you are given this type of problem, thus evaluate integration this omega dv by 1 plus x square plus y square plus z square, where omega is the unit ball, x square plus y square plus z square less than or equal to 1. See, I am trying to plot this thing, x square plus y square or plus y square plus z square equal to 1. Okay, that is Desmos can only portray 2D things. Okay, so this is nothing but r equal rho equal to 1 spheric sphere. Here theta varies from 2 pi 0 to 2 pi, phi varies from 0 to pi, and that is the Jacobian is dv is rho square sin phi d phi d theta d rho. You integrate with respect to phi, theta and all, and that is rho square by square root of 1 plus rho square. Integrate them and you will get the desired answer. Similarly, there are problems, more problems. There are also questions on solids of revolution, volume of solids of revolution. Solids of revolution nothing but when we rotate some curve or around some axis or some straight line, then we get volume of solids of revolution. These things I will like upload in the notes and you will easily check it out. There are some more problems on surface integrals and surface area of the cap obtained by cutting the hemisphere by the cone. So there are many problems on surface integral, and I think you can check them out. That I will upload these notes, no problem. Okay, let's me just remember the engineering mathematics 1 syllabus. Okay, I think these things are not in your syllabus. Now this note I will definitely upload in my Google Drive link. Now I will just give you some basic idea about what does we mean by saying vector space, because vector space is in your syllabus. So that is some linear algebra. And first okay, I think you have all watched the slides by Professor Jitendra Kumar, and there are some slides which I made for you. Now suppose that v1, v2, vn and v are vectors are in Rm. Now what do we mean by saying linear combination? We say that v is a linear combination of v1, v2, vn if there exist scalars x1, x2, xn such that v equal to x1 v1 plus x2 v2 plus xn. That means that we say that a vector v, that is linear combination of another vectors if v1, v2, vn, if there exist quotable scalars x1, x2, xn such that v can be expressed as a linear sum of those vectors. Geometrically, the linear combinations of a non-zero vector form a line. The linear combinations of two non-zero vectors form a plane unless the two vectors are collinear, in which case they form a single line. Expressing a vector as a linear combination. See, let B denote the matrix, those columns are v1, v2, vn, expressing v equal to x1, v1, x2, v2 plus xn, vn as a linear combination of the given vectors is then equivalent to solving the linear system vx equal to v. মামা আমি পরে ফোন করছি, হ্যাঁ আমি এখন অনলাইনে ক্লাস নিচ্ছি। So see, we express V as a linear combination of V1, V2, V3 in this case. So see how you have to solve it. So first V is 3 to 4 and this V1, V2, V3 is this. So just write 3 to 4 equal to x1 into V1, x2 into V2, x3 into V3, and then you communicate the likewise terms. And if you do this, you will get relation in x1 and x2. Then just solve it and you will get that how this V1, V2, V3 are linearly combining them, you are getting V. Now linear independence. So see, if n vector in any vector space V that can be written as a linear combination of other vectors, then we say that V, the vector V, is linearly dependent upon the other vectors V1, V2, V3. Now if the same thing does not exist any suitable scalars, that means that if there does not exist any x1, x2, xn such that V can be written as V equal to x1 V1 plus x2 V2 plus and so on plus xn Vn. See here, if you try how to check that this V1, V2, V3, V4 are linearly independent, just write x1 into V1 plus x2 into V2 plus x3 into V3 plus x4 into V4 equal to 0, the null vector. And now you have expressions for V1, V2, V3, V4. You can solve them for x1, x2, x3, x4, and if you get not trivial solution, that is x equals to 0, x1 equals to 0, x2 equals to 0, x3 equals to 0 and x4 equals to 0, then you can say the vector are linearly independent. And if you get V1, V2, x1 as a other than any trivial solution, you get some non-trivial solution, then you can say that they are linearly dependent. Now there are also one concept of span. Suppose that V1, V2, Vn are vectors in Rm. Now span means the set of all linear combination V1, V2, Vn is called the span of these vectors and is denoted by span of V1, V2, Vn. If the span is all of Rm, we say V1, V2, Vn form a complete set of Rm. Okay. Now there is one basis of Rm. Basis of Rm means a basis of Rm is a set of linearly independent vectors such that forms a complete set for Rm. That means a basis is the smallest generating set that is linearly independent, and every basis of Rm that contains m vectors. Now these notes will be effective for you when you will try to understand this basis and dimension and all. Now subspace in set we have subset, but in vector space we have the concept of subspace. Okay. And what is basis and dimension? A basis of a subspace V is a set of linearly independent vectors whose span is equal to V. If a subspace has a basis consisting of n vectors, then every basis of the subspace must consist of n vectors. We usually refer to n as the dimension of the subspace. There are also concepts of column space, null space, standard basis, how to finding basis for the column and null space. That is just for your reading purpose. You just go through this quickly. There are some notes. So how to determine the null space? If you have a one matrix, you can determine the null space by, see, if you want to the null space of this, you have to just write 1 0 minus 2 3 0 1 minus 4 1. You have to put one vector here, x1, x2, x3, x4. Then you multiply this r with that vector and you solve these two equations. So there are four unknowns and there are two equations. So you can take x3 equal to 0 and then solve for x1, x4, and that is how actually you can, or you can use the pivoting technique. That is how you can solve the nullity of the matrix. So that is definition of vector space. I strongly recommend of you guys to go through the book by Gilbert Franz, and from if you want to know linear algebra from scratch, then I am suggesting you to watch this this lecture. I am suggesting you to watch this lecture. I am suggest okay. And if you are like, I am suggesting you some books, and this book is actually very helpful. Gilbert Strange, Linear Algebra and Application. This book is very useful for you. This Linear Algebra and its Application by Gilbert Strange. That is a very nice book. And also you can watch the videos. The videos are available in YouTube by Professor Gilbert Strange, and you can also watch those videos by Professor Gilbert Strange. There are some videos by Professor.
Subject. Type an in-call message, sir.
So that is actually the course by Professor Gilbert Strange, and you can see that his like matrix, multiplication, this pivot variables, independence, basis, dimension, 4 fundamental subspaces, everything you will just get to know from Professor Gilbert Strange this video. That will be very much effective for you also, and he is one of the finest linear algebra teacher of the world. So you can watch how Professor Gilbert Strange is presenting. Okay, I'm writing once again.
Write an in-call message, sir.
There are several books written by Professor Gilbert Strange. There is also one new edition. That is the book. Introduction to Linear Algebra, Professor Gilbert Strange. That is the in the next class I will actually teach you that about what does it mean by saying eigenvalues and eigenvectors, and how to determine the eigenvalues and eigenvectors and those problems. I will try to solve on eigenvalues and eigenvectors. I will upload the notes on also. That will be some notes on eigenvalues that we can actually learn from a lot. So you can search like linear algebra Gilbert Strange. That is the book. You can try. And okay sir, if you do you have any questions, and if you have any questions, then I am thank you for joining my class.